Hello academic stars, welcome back to Caltex Academy. Today we are looking at shortest distance between 2 points on Earth surface close together. In our video number 1, we look at in general introduction to Earth geometry and we develop some formulas, but there was a demand from one of the academic stars that I should clarify the formula for getting shortest distance. So today we are looking at that derivation and perhaps we will have some simple question to illustrate the shortest distance, especially for 2 points on the same surface close together. So let's have a sketch of the Earth. Like we might have something just rough. If this is the model of Earth with the South and North Pole, we can estimate our latitude, that is the equator, at this middle of the Earth with its center here aligning at the same axis that passes dividing this into eastern and western hemisphere. We can take a certain latitude, maybe in the northern hemisphere. For instance, if this is what we have taken to be the latitude and if it goes across to the other side, of course we know a center for this can be given there. We can call this as C, as this one is O, and this is 0 degrees east, and that is the equator. We have here also 0 degrees west. And let us draw two longitudes also. One is in the western hemisphere and then the second one is in the eastern hemisphere. And we have this looking like that. Now you can see it has passed through this point and we can call this as point A. Now we can draw another longitude somewhere here also where it intersects with our latitude. So we can maybe call this one here 50 degrees. Okay, let's say 60 degrees in the northern hemisphere. So we can call this point B. So if we extend from here our A to the center C and also extend our B to the center C, we will have certain angle extended, and that is the angle difference between the two longitude of this side here. Maybe we are going to give some degrees for this longitude lines. Perhaps we may say this is 40 degrees in the western hemisphere. Meanwhile, this one is 25 degrees in the eastern hemisphere. And from there, our main interest is to get the shortest distance between this point A and B. So we can draw a line exactly like that meets in straight line. And for now, since it is facing us, we may not see well, but we can redraw this diagram outside and we have something that looks like that. Like here, if this is our point A and this is point B, we can draw a straight line. You can see somebody who moves from this distance A to B using this route is shorter than somebody who moves from here like that. So that is why we call it the shortest distance. Now here is our center C. That is the extract of what we had here, A, B and C. So I brought it out for it to look clear. Now we can have this one dropped down to cut this line AB at this point, maybe N as the midpoint, and you can label this one as X. So the distance here is the same as the distance there. And remember this angle between A and B, we can call it maybe theta. So if this is halfway, meaning the angle also will be divided into 2, so we have theta over 2. Also here, theta over 2. And remember, in our derivation also we made last time, we said the smallest radius here, r, is given by the radius of the earth times cosine of this angle here, alpha. So, and alpha is this angle in which the latitude is in. So, what we have to do is to also represent the distance C, B, with that small r, and this small r is capital R, which is the radius of the earth, and the cosine of the angle in which our latitude lies. So this is also a small r. Now from this model, you can see that we can use trigonometry to calculate our shortest distance. How do we do that? Remember, this is at 90 degrees, or is right angle. So we have a triangle CBN with x as the opposite to this angle, theta over 2, and hypotenuse CB. So, from this mnemonic, where we say SOHCAHTOA, the one we can use is SHO, which is representing opposite and hypotenuse. So we have opposite hypotenuse, and our angle is theta over 2. So we have here sine of any angle like theta over 2 is given by the opposite, and from here our opposite is x over hypotenuse. Our hypotenuse is CV, that is r, cosine of angle alpha. So our main target is to make x the subject, meaning we are multiplying both sides by this. So we can have here, when you multiply this by r, cosine of alpha, also here r, cosine of alpha. We notice that this denominator will cancel and I left with only x. So if I arrange to have my x here, I will have gotten r cosine of alpha times sine of the angle theta over 2. So from here, remember the shortest distance is from A up to B. So if these lines are the same, meaning for us to move from A to B, we need to have move x plus another x here. This x plus the other x to double A, B as that distance. So if we sum these two x together, we obtain of course that 2x as our AB. But again we know that our x is this. So we can substitute in x with r cosine of alpha times sine of theta divided by 2. And this was the formula we quoted last time. It is derived just like this in this geometry. And from here, we can consider our degrees given for us here to be able to get exactly the calculation of the shortest distance between A and B. Maybe we can continue from here, and we have AB as twice. So R is the radius of the earth. For now, I'm going to use it as 6,400 kilometers. So we shall multiply this by 6,400 kilometers times cosine of our alpha, and the alpha is this 60 degrees. So we can have our 60 here degrees, and we multiply by sine of theta over 2. But what is theta over 2? So first we need to get our theta here, and theta is calculated from, since these two lines lie in different hemispheres, that is western hemisphere and eastern hemisphere, then we have to get the angle difference by adding these angles together. So we'll start with the one in the west, that is 40 degrees, plus the eastern hemisphere has 25 degrees. If we add it together, we can obtain as 55 degrees, and we place it here as 55 degrees, but remember it's divided by 2 from the formula we had. And from here, we can make our calculation. Maybe let's get a calculator and work out once. So from here, we have 2 times 6,400 times cosine of 60, and we close that bracket. We also multiply this by sine of. Now we can make this as a fraction, that is 65 over 2, and we close the bracket, and we have here our answer as 3,438.717,493 as the answer, and we can approximate it to 3 significant figures. So since this number is beyond 5, we can round 1 and add to 3 to make 4. So our shortest distance is approximately to 3,440 kilometers. So if you are not calculating the shortest distance, then it will be this curve that moves like that, which is this one here. And that curve, you can go ahead and prove to yourself by calculating. You realize that the answer between A and B using the curve is more than our distance here, and that is why we refer to as shortest distance between 2 points on Earth's surface close together. The next time we shall look at the shortest distance of points that are far apart from the Earth's surface. So thank you for watching this video, and see you in the next video, where we're going to look at the next approach of distances between bodies that are maybe opposite in the other hemisphere. So see you in that video. Peace out.